A very good morning to our panel 1, Dr. Aidil, and our panel 2, J. Harris. Today, I'm going to present my final year project titled Examination of the Influence of the Semi-Vertex Angle and the Rigid Edge Support on the Buckling Behavior of Steel Cones and Cylinder. My project supervisor is Dr. Olavale. Dr. Olavale. Next slide is explain about the content of my presentation. First is the introduction. Second, I explain the literature review. Third is problem statement. Fourth is objective. Fifth is scope. Sixth is methodology. Seventh is the results and discussion. And eighth is the conclusion. Now I start with my introduction of my project. First, conical and cylindrical shell structures are widely used in many branches of engineering such as aircraft, nuclear reactors, storage tanks, pressure vessels, pipelines, and offshore drilling rigs. Second, structures are subjected to different loading conditions such as axial compression. Under these loads, the buckling strength of cone and cylindricals becomes one of the crucial design considerations. Third is the instability of the structure is one of the factors that limit the extent of which the structure can be loaded or deformed. Finally, this project research is mainly focuses on semi-vertex angle and the rigid edge support of the buckling behavior of steel cones and cylinders subjected to axial compression. Okay, this slide is explain about the literature review. This slide is compare my research compared with the other researchers who done before this. First is in 2012, Plachut and Fiafumi, and the 2015, and then 2017 Fiafumi, and last one is my column. We can see that the first three researchers conduct the experimental and numerical. Me, I'm conduct the numerical results only. Second, the thickness of shape from in the past researchers in 2012, 2015, and 2012 and 2015, they used the thickness of shape is 2 mm mild steel. In the 2017, they changed a little bit is 2.89 mm, and for me, I use 1 mm mild steel. Second, the yield stress. Yield stress for every past researchers for 2012, 2015, and 2017, their uses 230.6 megapascal. It depends on the thickness because they're using the 2 mm thickness, so the yield stress is they use 230.6 megapascal. For me, is I'm using a 1 mm thickness, so I'm using 156.55 megapascal. Yield stress is a it's fixed for the mild steel. It's a mild steel property. It's range from uh, 150 until 250. The next is the semi-vertex angle. The angle used in 2012 is they are using 26.56 degree. In 2015, they used 0 degree, 5 degree, 10 degree, 20 degree, and 30 degree. In 2017, they used 30, 50, 60, 70 degree. I'm using 0 degree, 5 degree, 10 degree, 15 degree, 20 degree, 25 degree, 30 degree to determine the collapse load and the buckling behavior. Radius, they are change the bottom radius. Uh, Change the bottom radius. For me, I'm used the fixed radius. I'm change the top radius. Next is the problem statement of my project. First is steel structures are normally suffer from various types of damages, while in service such as corrosion or fatigue, cracking are related to age. But others here are more likely to be mechanical damage caused by accident, loading, or impact. Second is a buckling is one of the main failure consideration when designing a structure. Due to widely use of shell structure, it is important to study about the failure module of the safety threats. And last one is a plastic buckling of the conical shell. Semi-vertex angular rigid support have not been researched extensively. When we see the introduction before this, they also there also a key point, the problem statement where the structures are subjected to different load condition. Under the under the disload, the buckling of the strength of cone and cylinder becomes one of the crucial design consideration. The various of the different kind of load uh, affect the affect the structures, affect the structures, affect the structures. And then this is an example of the buckling of the major in the offshore and onshore structures. For example, first is a buckle offshore pipeline. We can see the buckle in the middle of the pipeline, and then second one is a buckle of an oil rig platform. The buckle of the basement causes the oil rig platform collapse, and then the third one is a buckle of the onshore pipelines. This is one of the example. We can see the buckling of the structures. Okay. Next, I explain the objective of my research. First of my objective is to investigate the effect of semi-vertex angle and rigid edge support on the buckling behavior and load carrying capacity of the shaft. Second, to stimulate the cylinder and cones with a different semi-vertex angle using abacus finite element probe. This is my scope of my research. First is that this research consists of one cylinder geometry and a four conical geometries are different using a different semi-vertex angle using 0, 5, 10, 15, 20, 25, and 30 degree different cone angle uses research. Using a 1 mm mild steel plate to determine the buckling behavior and load carrying capacity of the shell. For the FIP1 and FIP2, we conduct the numerical findings with the finite element abacus, and finally we compare the finally the comparison between numerical and theoretical calculation will be conducted. Okay, methodology. Methodology methodology of my research. I'm using abacus software to conduct my research to get the numerical result. So these are the steps in the abacus we need to consider. First is making parts. Second is making property. Making parts we can see in the next slide. First one is making parts. Second we need to do making property. This is making property. Second picture explain the making property. Third is making assembly. Third picture explain the making assembly. The fourth is create step. Fourth is a create step picture. Fifth is create constraint. Fifth picture explain the create constraint, and then the sixth picture create load. Create load. In the create load, we to fix the boundary condition and the load. Fifth picture is a mesh picture we can see in here. Create mesh, and last one is create job. Create job is to determine the collapse load result. Okay, this slide explains the result and discussion of my research. Okay, we can see that there's a this result, and this is a numerical results for 0 and 5 degree, 10 degree, 50 degree, 20 degree, 25 degree, and 30 degree using a yield stress 156.55. First, beside the thickness F numerical collapse load, this is my result I compare with the previous research results done by before this. When we can see that For 0 degree, there's a 59.25 kilonewton, 5 degree is 53.81 kilonewton, 10 degree 47.60, 15 degree there's a 40.88, 20 degree cone is 33.28, 55 degree cone there's 25.61 collapse slope, and 30 degree is 17.88. We can see that when the degree is increases, the degree in the structure increases, the 0 degree, 5 degree, 10 degree cones, we can see that the collapse load is decreases. So when the degree when the degree is higher, the collapse load becomes lower. When we can see that the previous research showing the same results, that when the degree increases, the collapse load comes decreases. This is the deformation pictures for every angle. We can see that the deformation for 0 degree, 5 degree, 10 degree, 15 degree, 20 degree, 25 degree, and 30 degree. Okay, this graph explains the force and displacement graph for every each degree. For every and each degree, you can see that the highest point for 0 degree is 59.25 something, and then the 5 degree is 53.81, for 10 degree 47.60, for 15 degree is a 40.68, 40.88, for 20 degree is 33.28, for 15 degree is 25, and for 30 degree is maximum point is uh, 17.88. 17.88. This graph also explains the maximum point. The maximum point means the highest collapse load which the every degree can withstand the load. The highest collapse load which every degree can withstand. The next results and discussion is explained about the theoretical results and numerical results. Theoretical results is calculate manually using formula 2 pi r1 t yield stress cos beta. 2 pi is a fixed, r1 is a top radius, t is a thickness, yield stress is 156.55, cos and beta is degree. It depends on degree. When you use 0 degree, you get the value. Okay, now we can compare the numerical value and theory value. 59.02. The last column is explain the percentage error between numerical and theoretical error. We can see that 0 degree obtain less error compared to the 30 degree, which is a 46.67 percent of error. This error maybe there is a error, or maybe the error in the numerical readings, when the measurement the when measuring the numerical readings. For example, the for F theory, for sometimes the parameters are different, or the it will or the numerical when the mesh when we create the mesh, when using a lower mesh, there will be a slightly different with the theoretical and a numerical reading. These are the small causes. There is a small causes the percentage of error between F theory and F numerical. F theory and F numerical means collapse slope between theory and numerical. Last is conclusion. Conclusion, first conclusion, the numerical data on the effect of semi-vertex angle on the buckling of cylinder and the cones has been presented in this research study. Specimens of different semi-vertex angle were subjected to axial compression using a different parameters. Second, the changes in parameters proven that the semi-vertex angle does affect the load carrying capacity of the shells and motors. When there is a changes in the parameters means when we change the radius of the top or and then the yield stress, there is a different there is we can see the difference between the readings when we reduce the angle. When we can see that when we increase the angle we can see that the collapse load become decreases. That's explain the second conclusion. Third is the average collapse load for zero cylinder is 59.25, whereas the average collapse load for 30 cone is 17.88. The collapse reduced as much as 70% when shell with lower semi-vertex are compared with the shell with higher semi-vertex angle. Yes, these 2 points explain the same is when the angle increases, the collapse load starting to decrease. So we can conclude that when we design the structures using a higher vertex angle, the collapse load will be the collapse load will be the collapse load will be higher than it can withstand the higher load. Thank you.